Jim Freerick. He's going to talk about quantum mechanics and if we should trade off mathematics and conceptual understanding.
Or abstraction. Abstraction, yes. Okay, thank you very much. I start off all my talks, I have a number of colleagues in Ukraine. I start off all my talks with a moment of silence, so I would request just a moment of silence for the people in Ukraine. All right, thank you very much. What are the different ways that we should teach quantum? How should we teach quantum? A lot of you might be thinking about this. And historically, there are two choices. There's the matrix mechanics of Heisenberg, which in the original form, no one teaches. But a lot of people, if you think about spin first, you're starting off with matrix mechanics. Or there's Schrodinger's wave mechanics. But I'd like to argue that there's actually a third way that I like to call operator mechanics. And this was originally worked out by Pauli when he first solved for hydrogen. It's often described as a matrix mechanics solution, but if you look at it, there are no matrices in the paper at all, and he's actually talking about just manipulating operators. And this is what Dirac said in Dirac's famous paper where he talks about Q numbers and C numbers. He's also talking about manipulating operators. But the real star of this show is also Schrodinger, who in 1940 showed how you can use operators to solve quantum mechanics problems in exactly the same way as we solve harmonic oscillator, but for every one of the exactly solvable problems, particle in a box, isotropic oscillator, hydrogen, etc. They can all be solved in a very similar way. Now, when you teach via operator mechanics, you lower a lot of the calculus math load. We already heard in the first talk that calculus is not so simple for students to be able to master and work with. And if you teach quantum mechanics in the conventional way, they have to really become experts in calculus. In this way of teaching it, there are no differential equations, there are no Dirac delta functions, and there are almost no matrices. Everything follows from four fundamental operator identities. I'll be showing you some of these when I talk about the example that I'm going to give you, and I say I spelled Leibniz's name wrong. The Leibniz product rule for commutators, the Hadamard lemma, the Baker-Campbell-Hausdorff formula, and the exponential disentangling identity. The first three, many of you might know. The third one, or the fourth one, you might not be so familiar with. I'm not going to actually be using that one in the remainder of the talk. But it is abstract, and so you have to get students to be able to be comfortable with abstraction. And the way that I do it when I teach the course is we build in the abstraction relatively slowly, first starting with conceptual ideas, then moving on to how do I represent those conceptual ideas with a formalism, and then eventually moving into operators and how to work with operators. So let me illustrate for you how we do this to get the harmonic oscillator wave function using just operators. So I'm going to start with something that I hope everyone in the room is familiar with. This is the way we write the harmonic oscillator Hamiltonian in terms of the ladder operators A and A dagger. This is what A is. A dagger is the Hermitian conjugate. The nth energy eigenstate can be written as 1 over square root of n factorial, A dagger to the n acting on the ground state, and the ground state satisfies this condition. So the first thing that we're going to be doing is going to use this Hadamard lemma to rewrite the raising operator as a similarity transformation with respect to a Gaussian operator. So if you're familiar with the Hadamard lemma, the first term is the p operator in the center. The next term is the commutator of x squared with the p operator, which gives you an x, which is going to be the x term. The third term would be the commutator of x squared with that commutator, which is x, and that commutes. So the Hadamard lemma terminates after two terms, and you can trust me, I got the constants right, that actually gives you the raising operator. Similarly, the lowering operator is just gotten by taking the Hermitian conjugate of that. Now, I can use this top expression here when I write the lowering operator in this fashion to show that the p operator annihilates this state. And that's actually a very important point that we're going to be using. Okay, so we start with the nth energy eigenstate. We rewrite this operator in the center in terms of this similarity transformation, and if you notice, there's the e to the x squared, which will sit right next to e to the minus x squared when I do a product of these, and those factors are going to cancel, so they only sit on the outside. Now, the next thing that we do is we want to introduce this state that is annihilated by the p operator. So I just take this e to the minus 1/2, it's got to have an e to the plus 1/2. So I write it as e to the minus a full times e to the plus a half. And now, because the p operator annihilates against this state here, this combination, the operator acting on the state, that means that I can take one of those p factors and rewrite it as a commutator, because when the p side is acting on that state, I'm just adding 0. And then I can repeat that, and you can get all of these into an n-fold nested commutator. Now, if you want to go back to your calculus, I don't do this with the students, but if you remember, p operator is like a derivative. This is like the n-fold derivative of that Gaussian factor multiplied by the opposite Gaussian factor. And if you remember the Rodrigues formula for polynomials, this is the Rodrigues formula for the Hermite polynomials. But you can derive the fact that it's a Hermite polynomial by evaluating what this is for the zeroth, n equals 0, for n equals 1, that gives you the starting point, and you can actually work out the recurrence relation just by working with commutators, so you don't need to introduce the derivatives or even look up what a Rodrigues formula is in order to determine the recurrence relation. And you end up with this. It's a Hermite polynomial of a position operator. The argument is a position operator inside here. Okay, so we're getting real close now. To get the wave function, I have to multiply by the position bra. And now you notice that this x operator acts on the position bra. Because the position bra, the x operator is position bra is an eigenstate of the x operator, I can replace the x operator by the x eigenvalue, and then that becomes a number, and I can move it out of the matrix element. And now I have to calculate the wave function of the ground state. Now, the way that we do that is I call this multiplying by 1 because I want to introduce this state that's annihilated by p. You can see that these two factors are opposites of each other, so they multiply by 1. I'm going to take this one and operate it against the position bra, and I can then pull it out, just like we did before. And now for the position bra, I'm going to rewrite it in terms of the translation operator acting on the position eigenstate at the origin. But this p operator annihilates against that state to the right, so the exponential of it gets replaced just by 1. And now the x operator can act on the position eigenstate to the left, but it's evaluated at the origin. So x acting on that just gives 0. So that exponential gets gone and it becomes 1. And now I just have a normalization constant to work out. And of course, we all know what that normalization constant is. We can plug that in. And there you go. We've just calculated the wave function of the harmonic oscillator without any calculus whatsoever. So you do not need differential equations to do quantum mechanics. So using abstraction lightens the mathematical prerequisites that you need. And I think that this is very important if you start thinking about trying to introduce calculus to a broader audience than just physics students, as we want to try to educate more people to be working in quantum information science. But you have to be able to develop the abstraction at the same time. If you try to throw a problem like what I just showed you on the first day of your class, you're going to have everyone walk out of the room. But you can build up to it, and if you build up to it, they're able to do this kind of work. Now, this also allows us to cover a lot more physics. Most quantum mechanics classes now, I would say at least half of the class is teaching math. Well, we're physicists. We shouldn't be teaching math. So if you do things this way, you can actually cover more physics and more experiments. So I just made a word cloud of the different experiments that I cover in a one-semester class, and I cover things that you might not. I don't know if I can get this. There we go. I cover things like E2E spectroscopy, which allows you to visualize the wave function of a hydrogen atom in momentum space. I cover LIGO. We cover things like Hambury, Brown, and Twist, proton charge radius, delayed choice experiments, and many, many other experiments that normally people don't cover in a traditional quantum mechanics class. And these are the really interesting modern experiments that we need to cover to help train people for the 21st century. So with that, I'm going to end and going to just thank the funders. And also, if you want further information, I have a website that covers my quantum mechanics work. And I have 2 courses that are on edX. One of them is an undergraduate quantum mechanics course that works in this sort of mode, and the other one is a course that teaches conceptual ideas of quantum mechanics for everyone. It's called Quantum Mechanics for Everyone. So thank you.
Thank you.
Thank you. I intuitively have a sense that this is mathematically complex and that it would be for my students. And so I'm wondering if you have data or experience that shows that like students find this easier than talking about matrices.
Yeah, it's always hard to know what easier is. What I will say is that I feel many students don't really learn much in a quantum mechanics class. So I think already the bar that we have to get above is pretty low because we essentially teach exactly the same thing to undergrads as we teach to graduate students because they didn't really get it the first time. Now, what I will say is that I have taught this class on edX. edX, I typically get about 1,000 students enrolled in the class each time I teach it. So that's been about 2,000 students. Not everyone completes the whole class. And I've taught it twice now as a for the undergraduate students in my classroom. I don't have comparative data because I'm not teaching it the other way at the same time. But I don't have a situation where students are acting as if they don't understand anything and they need to walk out of the classroom. They tend to do fairly well on exams, and they tend to be able to do this. Again, you have to work it up to it slowly. You can't start with something like this. But if you work up to it, they're able to handle the kind of abstraction that they need.
Thank you.
How long does it take you in the semester to work up to what we saw here with the wave equations?
So I do 4 weeks teaching conceptual ideas before I really start introducing formalism. I think it's really important to understand the conceptual ideas of superposition, entanglement, measuring, a concept I call tagging, and complementarity. So once you understand those concepts, then building in formalism to go with it and building in operators becomes much easier to follow.
All right, thanks.
Hi, I'm curious about, I'm having trouble thinking about how we would get from this as an undergraduate instruction to, say, graduate level instruction. So I'm thinking about if you think about the goal of an undergraduate quantum mechanics course to prepare someone to take a graduate level quantum mechanics course, how do you think someone might transition into graduate level instruction after a course like this?
So what I would say is that if you ask most people who go into advanced quantum mechanics in graduate school, working with operators is far more important than differential equations, because if they're going to go into field theory or many-body physics, that's what they're going to be working with. So I think building operator sense early is really important because, frankly, we never solve anything in graduate school or research, almost never, that involves solving a differential equation by a series solution. So we're teaching a lot of stuff that students don't really use.
Okay, thank you.